The next example we look at here in factorising polynomials is this problem here, 6z to the power of 4 plus z squared minus 1, where z is a variable within the set of complex numbers. Okay. Now our solution, to simplify this, we're going to let w equal z squared. So 6z to the power of 4 plus z squared minus 1 changes to 6w squared plus w minus 1. Now this one here we can see, we can factorise that. Okay, so whilst we don't always have to use completing the square, if it's factorisable, okay, so we obviously first look to see whether we can factorise it as real, like we would with real numbers. Okay, so this one factorises to 2w plus 1 times 3w minus 1. Having done that, we'll substitute back in using our w equals z squared. So this is the same then as 2z squared plus 1 times 3z squared minus 1. Okay, now 2z squared is the same as root 2z all squared, and plus 1 is the same as minus I squared. Doing that so that we can factorise this further, okay, as a difference of two squares. Root 2z minus I, root 2z plus I. This one here is already a difference of two squares, okay, which is root 3z minus 1 root 3z, that should have in there, plus 1. Okay, and put our z in there as well. Okay, so that's it fully factorised. And you would expect that, okay? We have here power of 4, so we should have 4 factors over C. So if we just go back up in our notes to the top here, the first sentence that says there is that a polynomial of degree n has n linear factors over C, over the set of complex numbers. And so a polynomial equation of degree n will have n complex solutions. Okay, and that's what we find with that example. Our polynomial has a degree of 4, and so we would expect there to be 4 linear solutions, and that's exactly what we've got. 2 are real, okay, these 2 here are real, and these 2 are complex. Okay, but there are, whilst we say these are real here, they are also complex, because remember, real numbers are part of the set of complex numbers. But specifically, these are real, aren't they? Okay, but there are 4 complex solutions. Okay, let's go a little bit further. The next one, find all factors of p of z if p of z is equal to z cubed plus 7z squared plus 16z plus 10, where z is belongs to the set of complex numbers. Now the first thing we're going to do is to use the factor theorem to find a linear factor of p of z. Okay, because remember, when we're factorising cubics, we first need to use a trial and error to find a linear factor, then we divide into our polynomial to obtain our other factor. Alright, so we're just going through trial and error. We find that p of negative 1 gives us a value of 0, which means that z plus 1 is a factor. Okay, this is just coming back to our factor theorem. Okay, z plus 1 is a factor of p of z. We know that by applying the remainder theorem. Okay, negative 1 in place of z gives us a value of 0. So in other words, there's no remainder. If there's no remainder, z plus 1 must be a factor. Now, to divide this factor into p of z, okay, we need to be able to do long division of polynomials. Now in this particular case, synthetic division will work, because we're dividing by a linear expression, okay? But sometimes we need to divide by quadratic expressions, and synthetic division becomes messy, okay? And So I'd just really encourage you to master the long division and to be able to do that. Okay, now you're doing our long division. Remember, we divide z into our first term, z cubed. That goes z squared times, because if we were to multiply them together, we'll get z cubed. And that's the next thing we need to do. We need to multiply z squared by each of these terms. That gives us z cubed plus z squared. Then we subtract, okay? Subtracting z cubed from z cubed gives us 0, so we just leave it blank. 7z squared minus z squared gives us 6z squared. And then we repeat the process. Z into 6z squared goes 6z times. Then we multiply. 6z times z gives 6z squared, and 6z times 1 is 6z. Subtracting, we end up with 16 minus 6 is 10z, and then bring down the 10. Okay, so remember, we're dividing, then we multiply, then we subtract, and we bring down our unused terms. Okay, so we bring down the 16z here. Now we're bringing down the 10. 10z, okay, z in 10z goes 10 times. Then we multiply 10 by z is 10z. 10 times 1 is 10. Then we subtract, and we can see by dividing it, we have a remainder of 0. Okay, this is our remainder down here, and that's the end. So if z plus 1 is a factor of our polynomial, then z squared plus 6z plus 10 is our other factor. But that is a quadratic factor, so we need to factorise that as we did in the previous example. Okay, looking at if we can factorise it. Now that doesn't factorise nicely, so we have to complete the square, and by doing that we are obtaining this result here. So I encourage you to work through that, completing the square process, to make sure that you get this result. Okay, z plus 3 minus I, z plus 3 plus I. And so we are able then to write P of z as the product of our linear factors, z plus 1, z plus 3 minus I, and z plus 3 plus I. And that's our solution for that. Then we're going to move on to the conjugate root theorem. Now, the conjugate root theorem just says that if a polynomial has real coefficients, okay, and that's really important, it only applies when the polynomial has real coefficients, not complex ones. Its roots are either real numbers or occur as pairs of conjugate complex numbers. For example, now a pair of, well, let's just make sure we understand what it means. A pair of conjugate complex numbers would be 3 plus 4i and 3 minus 4i. Okay, they are a pair of complex conjugate numbers. Okay, because they are conjugates of one another. So let's look at this example. If 5 plus 5 root 2i is a 0, or a root or a solution to P of z, which is given by this polynomial, find the other two zeros. Now if 5 plus 5 root 2i is a 0, okay, then its complex conjugate will also be a 0, because in this particular case our polynomial has real coefficients, so our conjugate root theorem is going to apply. So in other words then, 5 minus 5 root 2i is also going to be a 0. Okay, and thus our factors that relate to these zeros are going to be z minus 5 plus 5 root 2i and z minus 5 minus 5 root 2i. And the next step involved in this problem is to multiply these two factors together to obtain a single quadratic factor, which may then be divided into P of z to obtain the third and final factor, and hence the last 0. Okay, multiplying them out, okay, this is a difference of two squares, okay, and so we have z minus 5 squared and 5 root 2i squared, and so we then, changing this, becomes 50, and so then we can expand that and simplify that nicely. This is our factor. So just expanding this out, take note of how this is done. This becomes our quadratic. That is what we need to do then, is we've got our factor, dividing that into our polynomial using our long division method gives us our final linear factor of z plus 2. Okay, make sure you can work through this problem. Okay, if you've got any problems, then come and see me. We're dividing that in there. We've got then our linear factors are given here, and so the zeros are 5 plus 5 root 2i, 5 minus 5 root 2i, and negative 2. So then, make sure you work through that, you can understand that fully, then you can go on and do exercise 3F and 3G from your textbook.